Today the topic of our lecture is problem 10.23. In this problem we have a holding fixture that is used to hold or clamp our piece of 37.5 millimeter thickness. This is the holding fixture, this is the workpiece, and this is the thickness of workpiece, which is 37.5 millimeter. Here if you see, this is the spring, and this spring has been deflected through this clamping screw. When this screw is fully tight such that this workpiece cannot move out of this clamp, then at that point the spring length will be equal to the length of the workpiece, and at that point if you want to remove this workpiece you will have to unclamp this screw. When you start unclamping this screw, at that point the spring will exert a force outward that is equal to 45 Newton force. So this force will be equal to the force that will be exerted by this screw on this spring. Now after that we are given that the screw is M10 cross 1.25 threads. Here the important thing that needs to be considered as this strength, this is the diameter of this screw. If you see over here, this is the screw and this is how a spring is inserted into it. So if you see over here, this is the clearance between this screw and this spring. So this clearance is 1.25. This is the diameter of the screw. The free length should be less than or equal to 48 millimeter, and the solid length of the spring should be equal to or less than 31.5 millimeter, and solid factor of safety should be greater than or equal to 1.2. Here it is given that the design of the spring should be started with the wire diameter equals to 2 millimeter. You will have to start with it. Then the material should be selected to be a 227 hard-on steel, and the available wire diameters are between these. As you are given that you will have to start the design from 2 millimeter and you will have to go with 0.2 increment, means you will have to design the spring for 2 millimeter, then for 2.2, then for 2.4 until 3.2. And in the design what you will have to do is to select the wire diameter, and after that you will have to find out the internal diameter of the spring, mean coil diameter, and external diameter of the spring. Then this is C for the spring, and the number of active coils in the spring, the total number of active coil in the spring, the solid length of the spring, and L not critical, which will show you whether the spring will buckle or not, and solid factor of safety. So starting with the design, as it is given that you will have to select the spring with the wire diameter to 2. So internal diameter is equal to the diameter of the screw, which is 10, and you will have to add clearance with that. So 10 plus this clearance, that will give you 11.25. Mean coil diameter is equal to the internal diameter plus wire diameter, as internal diameter is 11.25 plus wire diameter is 2, so mean coil diameter is equal to 13.2 millimeter. Then after that you will have to find out the external diameter, that is equal to mean coil diameter plus wire diameter, so 13.2 plus 2, it will give you 15.2. Then we are required to find out the value of C for the design. It is equal to mean coil diameter divided by wire diameter, so 13.2 divided by 2, it will give you 6.6. Now you will have to find out the number of active coils, as it is equal to d to the power 4 g divided by 8 and 2 d cube k, as d is 2, so 2 to the power 4, and you don't know the value of g, so we will find it out from the table. Then divide by 8 into d cube, here mean coil diameter is 13.2, multiplied by k. So you don't know the value of k and g can be found from this table. Here you are given that the spring is this one, and for that if you see the d value of the wire is 2 millimeter, so when you want to convert it to inches you will have to divide it by 25.4, that will give you 0.0787, which is in this range, so g is 79.3, so put it over here. And now you will have to find out the value of k. So the value of K can be found from the equation that is F is equal to K into deflection Y. So divide the deflection Y over here, that will give you K is equal to F by Y. You know that the force that is exerted on the spring is 45 to hold this workpiece, divided by, and this Y can be found as free length L0 minus the length at the point of deflection. Means as at this point the length of the spring is 37.5 millimeter, so this is 37.5 millimeter, and consider this L0 means free length to be equal to 48. 45 divided by 48 minus 37.5, that will give you 4.29 kilonewton per meter. So put this value over here, so it will give you Na is equal to 15.9. Now you know the value of Na, you can find out the value of Nt, that is equal to Na plus 2, but that is based on a table for squared and ground in spring. This is their table. If you consider a spring of squared and ground ends, then the total number of coils will be equal to Na plus 2, and the solid length Ls will be equal to dNt. So Nt will be equal to 17 point, this should be also 13.25 and 15.25, then C will be equal to 6.625. Now let's find out Ls, and here you know that this wire diameter is 2 millimeter and total number of active coils is 17.9. So when you multiply it, it will give you 35.8 millimeter. Now let's find out L critical. For L critical, the value of alpha is 0.5 because the spring is supported between flat parallel plates. So instead of this mean coil diameter, you will have to put 13.25, and instead of this alpha, you will have to put 0.5. So it will give you 69.7. And you know that your free length is 48, so your free length is less than 69.7, so the spring will not buckle. But if it was buckling, still as there is screw inside it, so the spring will be safe. Now let's find out whether the spring will be safe under the condition when you bring this spring to the closure. So for that, you know that SSY is equal to 0.45 into SUT, and SUT is given by this equation, that is A divided by D to the power M. A and M can be found from this, as it was given that your spring is A227, so this is your spring, and for that the value of M is 0.19 and the value of A is 140. In fact, you will have to use this value for the 1783 divided by 2 to the power 0.19, so it will give you 1563. Then put this value over here, it will give you 703. Now you know the value of SSY, then you will have to find out this tau S as well, which is the stress produced in the spring when you force the spring such that its coils touch each other. So at that point, the stress produced in that spring is represented by tau S. Tau S is equal to Kb into 8 Fsd divided by pi wire diameter cube. You know the value of mean coil diameter D and wire diameter D, but you don't know the value of Kb and Fs. Kb can be found from this equation. So 4 multiplied by 6.6 plus 2 divided by 4 multiplied by 6.6 minus 3, that is equal to 1.214. Now you will have to find out the Fs. So for that you will have to use this formula, which is Fs is equal to K into Ys, but you don't know the value of Ys as well, and that can be found from this equation, that is free length L0 minus the length of the spring at the time when you force it such that its coils touch each other. Now L0 is 48, Ls is 31.5 millimeter, so it is going to give you 16.5. So you will have to multiply this 16.5 with K, which is 4.29. It will give you 70.8. So you will have to put this value and this value over here. That is going to give you 298.6. Now you know the value of tau S and SSY, so put it over here in this equation, so it will give you 5.2. so you are solid safe. And now you can use 2.2 2, after that 2.4. But since this is the best design, because if you see over here, this C value is in the normal range and A value is almost in the normal range, this value is almost in the normal range, and the spring is not going to buckle. Similarly, this solid safety is also better, so this design is best. But if you want to check, you can check it for 2.2 and 2.4 up to 3.2 and compare its results with this one. You will see this is better than the others.